So make sure your grades are up to date on Canvas. I'm pretty sure everybody should be up to whatever you submitted so far. If you haven't submitted everything, please submit it. I will grade it, or at least give you some points for your effort. So please do that. If you have any questions about, as I told you, when I'm grading these exams and homework, this is new to me, doing this Canvas grading stuff. So I'm learning. I think I'm annotating it and making comments. At least from my view, there's comments and stuff. I don't know what it looks like from your view. So hopefully if you have any questions about your grade or a problem, that you reach out to me and we can discuss it further. I'm assuming that you guys are seeing the annotations, but I'm not positive. A few of you have reached out about your score on exam 2, and I'd be happy to discuss that in more detail if you want. I'll email you back sometime this afternoon. Does anybody have a question about grades or the exam or anything? Going once, someone's chiming in, yeah. Yeah, I plan to, Heather. I should do that today. I meant to do it the other day. And don't forget, I mean, I know it sounds crazy because you just took a test last week, but our final class is a week from today. So that's the 30th, goodness gracious. And so the plan is to give you a final exam after class. So if you have an issue next Thursday and Friday with the logistics of the exam, you got to let me know now so we can work something out. I believe I have to have the grades submitted by Monday morning, so I can't give you too much leeway on how much time I give you to take the test. But the idea is to try to give you as much time as I can. So maybe I'll even post it earlier than Thursday. So Thursday you can ask questions and stuff like that. Does anybody have any questions about that? Yeah, so that's you're asking, is it cumulative? I mean, yes and no. There might be, look, I mean, you can't do the stuff we're doing now unless you can do the stuff from the first 2 tests. So it's cumulative in the sense that you have to understand how to compute derivatives and stuff. And it's possible that I ask you to do something that maybe is from chapter 2, but most of the questions will be from the perspective of chapters 4 and 5, if that makes any sense. So yeah, should you know how to take limits? Absolutely. But the problem's not going to just be compute this limit per se. You might have to compute a limit to do another problem, or as you're going to see today, we're going to talk about limits actually today, briefly. So, you know, am I going to ask you a question from chapter 1 or chapter 2? No. But if you don't know how to do the stuff from chapter 1, chapter 2, and chapter 3, you can't possibly do the stuff from chapter 4 or chapter 5. So I hope that's clear. Sometimes it is, sometimes it isn't. Okay. Any other questions? Did that answer your question, Heather? I don't know. So the next thing I wanted to open the door to is does anybody have a question about the homework, particularly, why is it not opening? Particularly problems 1 or 2. We didn't really talk about the other ones yet. but we have covered the necessary material for you to do problems 1 and 2. Okay, so you're talking about number 6 on homework 8. Yeah. Oh, yeah, did you email me about that? I think you did. I don't remember if I responded or not. Yeah, so this is an interesting problem. So on homework number 8, problem 6, it talks about Usain Bolt running the 100 meters in a certain amount of time. And using calculus, what we're trying to do is we're trying to figure out what is the maximum speed that he could have possibly attained during that race. So, you know, we're not looking for, what I'm looking for is to see if you can think about how you might apply some calculus. In particular, the mean value theorem. So here's the way I would encourage you to think about it. So let x of t equal the distance from starting line at time t seconds. So for example, we know x of 0 is 0. He hasn't traveled anywhere. And we also know that x of 9.8 is equal to 100, because at 9.8 seconds, he's gone 100 meters. So what this means, if we think about it from a physical interpretation, so this means his average, you know, velocity or speed. What is it? Well, it's total distance, so it's distance traveled, x of 9.8 minus x of 0. Distance traveled over time traveled, which is 9.8 seconds. So really, this is just your distance traveled 100 over 9.8. So if you go to a calculator and divide 9.8 into 100, you get 10, let's just approximate this as 10.2. Now, what are the units here? Because that's important when you're doing a physical sort of problem. And I know this isn't a physics class, but what are the units? Well, up top we have meters, so this is meters per second. Okay, now, okay, so what does this mean in the sense of what we've kind of been talking about? Well, let's put it in that frame of reference. So the mean value theorem says there is a time, which I'll call T star. I have to give it a name. Where it's greater than 0, but less than 9.8. And more importantly, when I plug that number into my function, which this might look scary to you guys because you're so used to seeing f as the name of the function. I'm just calling it x now, that's all. So what I'm getting at, and what the mean value theorem says, is the mean value theorem says precisely that at least at one point, you are going your average velocity. I mean, that makes sense intuitively, I think. So before we go any further, does anybody have a question about this so far? Going once, going twice. Okay, so okay, what can we, okay, so again, this is more of a thought exercise than anything. Can we gain anything from this? What can we conclude? So anybody have any thoughts? Can we conclude anything? By the way, it's worth pointing out for, and I don't know if this will help or does anything. You know, you can convert this to miles per hour. So this is this is meters per second, which is approximately 22.8 miles per hour. I mean, one conclusion that's obvious is that we hit our average speed at least once, but does that tell us anything about our maximum speed? So this problem is really getting to the heart of what do we understand about the mean value theorem? What can we gain from these particular sort of this relationship between a derivative and its average values? So maybe what we'll do is maybe I'll let you think about this. By the way, I'm not going to grade this particular problem if you're worried about that, Cami. But you know, I put this on here as sort of a thought exercise for those who want to give it deeper thought. So I gave you sort of an idea of how to think about it using the mean value theorem. And you know, if you want to talk about it further, we can do that at some other point. But I think it's more of an educational. It's more of an educational thing if I don't sort of say anything else and you ponder it on your own. I'm not going to put this like a problem on the exam or anything like that. It's more of something that we want you to think about. So one thing we could ask, if you wanted to take another hint, is there a solution to x prime of t greater than 10.2? Because if that equation doesn't have a solution, then you know that your max speed was at most 10.2. Now we don't, maybe it is, maybe it isn't, but these are the things that you sort of want to think about. Anyhow, I'll let you ponder that, and again, I'd be happy to discuss it further if you're still interested, Cami. But I don't want to waste. I don't want to say waste. The only way you guys are going to get anything from this particular problem is if you spend some time thinking about it and maybe drawing some pictures and messing around with some equations. Start with the mean value theorem and do some algebra. See what you can come up with. So I'll leave it at that. And then again, next week, if you want to come back to it, we can. Does anybody else have a question on this before we move on, or a thought on it? It's an interesting problem. Okay, well then let's move on. How about homework 9? Does anybody have? Does anybody have a question about homework 9 right now? 1 or 2? You'll notice I prefaced in homework 9 that it is long and a little challenging. So it's going to take some time if you want to do it all. And don't forget, no one ever said learning calculus is easy. We've always said it's a very time-consuming endeavor. It's also challenging. So. All right. All right, so then what we want to do now is we want to talk about these other problems on homework 9 that are what you guys call your word problems, or what some people call story problems or applications. So let's sort of come full circle that last class we spent time showing how useful f prime and f double prime are when analyzing a function f. So the first and second derivative have all these sort of, I don't want to say hidden properties, but they hold all the information. They're like the DNA of the function. So what we want to do today is we want to look at some more applications of these ideas. So what we're going to do is we start with what are called optimization problems. So what makes these types of problems difficult is because they're one of the things that's really challenging for humans. And that is, most of us learn a written and spoken language. For many of us in this class, it's English. Now, some of you might know other languages, Spanish, Arabic, you know, maybe some languages from other parts of the world. But you're also trying to learn this other language, the language of nature and science, which is called mathematics. And a very difficult thing to do is to translate English into math and vice versa. And you guys know that. You've probably struggled with that since you were school-aged, whatever that means. I know when I was a kid in school, that's one of the hardest things for me, and we called them word problems when I was in school. And you get these English sentences and you have to translate them into a mathematical formulation so that you can answer a question. Now, in the real world, what we call that is we call that mathematical modeling. We take a real world scenario and we formulate it in a mathematical way so that we can use the theory and all the good things that math gives us to answer questions. And so it's in our interest right now to sort of show you how that kind of works. So what I figured we'd do is we would do some of these homework problems to sort of help you along the way. So why do we call these optimization problems? I'm like struggling with my language today. It's very struggling. This is a much bigger, there's people whose jobs right now are in optimization. That is find, how can you think about this? Here's a better way to do this. Let's give you a bigger perspective on this. So given a situation and what we call constraints, determine the optimal solution. So that's a bunch of generic words, but that's exactly what we're going to do. So the best way to even start these is to just do an example. So let's look at something like on the homework. So I don't want to steal all the fun for you. So here's a typical problem. I want you to draw all rectangles. Draw out every single rectangle on the planet that have a perimeter of 300 meters. We want you to determine the one rectangle that has maximum area. So what we want to do is we got to think about this, and we got to think about the words and what they mean. If you want to solve this problem, you have to know what area and perimeter mean. So suppose we want to think about a solution. So it's going to take some work, lots of scratch work, lots of brainstorming. You're not, for most of these problems, you're not just going to write a solution down right away until you've done lots of practice. So the first thing you need to note it's impossible to draw every rectangle of perimeter 300. You just can't do it. You could draw a couple and you could maybe compute some areas. But that doesn't tell you how every single rectangle on the planet that has perimeter 300 is going to behave. All right. So what do we do then? Well, we need to draw a generic rectangle that has perimeter 300, and then we need to figure out which dimensions will give us the largest area. And you're going to say, well, how do we know if it's the largest area if we can't draw them all and measure them all? Well, that's the beauty of what we've just been spending time doing. The logical theory that is behind all the maximums and minimum stuff that we did the last few classes guarantees now, it guarantees in the future, it guaranteed 1,000 years ago which rectangle will have the largest area and which one won't. So that's what we're going to do. Let's draw a generic rectangle. So a generic rectangle will look like this. And so we can label creatively enough, we'll call this X and we'll call this Y. And we're given some information. Here's what we're constrained to. So the perimeter must remain fixed. The perimeter must be 300. But what's the perimeter? The perimeter by definition is the sum of the sides. So there's two sides of length X and then there's two sides of length Y, and we know that that must be 300. That's what we're told. That is our constraint. All right, now, what is the area of this creature? The area of this creature, so we have this piece of information that we can use. And then another piece of information that we can use is that the area is equal to X times Y. That's the area of a rectangle, length times width. And so if we read the problem carefully, we want to know which values of X and Y make A as large as possible. So that's our goal. Determine X and Y so that A is as large as possible. So turns out we can use calculus to do this, provided we formulate it properly. So let's be very clear how we can do this. So one way to do this is to determine a function for area and use calculus. Now, I didn't say it's the only way to do this. There's some other creative ways, but we're trying to teach you how we can do it systematically using calculus. The problem is right now is our area is not a function of one variable. It's in fact a function of two variables, X and Y. And that's not very helpful to us because we have only studied calculus in one variable. And so what we need to do is somehow figure out how to get a function for area. And luckily we can do that if we're creative enough. So that's what we're going to do. So to get a function, you can use our perimeter constraint. Now I'm going to write it slightly different. Up top, our perimeter constraint was 2x plus 2y has to be 300. Well, I can rewrite that. I can write that if I solve, for example, for y, I get y equals 300 minus 2x. And if I divide it by 2, I get 150 minus x. So I took my perimeter constraint and I said, okay, I'm going to try to make use of this. It's given to me. My problem is constrained to this. I am looking only at rectangles that have a specific perimeter. That is 300. And so I want to use that piece of knowledge to my advantage. What is happening? My kid is upstairs singing Justin Bieber. I'm ready to lose my mind. What kind of child am I raising? The joys. The joys. Okay, so here's what we're going to do. We have a relationship between x and y, and now we're going to take that relationship and put it into our area relationship. And what that does is that gives us a function. So if we, what do you guys like to say? Plug in to a equals x times y, we get a function. The area is now a function of x. It's x times, instead of y, I'm going to write 150 minus x, because that's equal to y. Remember, this is just y. So we can now use calculus. So I'm going to apply calculus. What's the derivative of a of x? The derivative is 150 minus, now that becomes x squared, so that's minus 2x. Thus, x equals 75 is a critical number. Here's what else is true. More is true. Since a prime of x, and then let me be a little more clear. Since the second derivative is negative, we know by the second derivative test that x equals 75 gives a local max. And then all it remains for us to do is verify it's the largest. It's a global max, and that's very straightforward as well, because what you have to do is you have to compare the area when the one side is 0, which doesn't make any sense, and then you got to compare with when the one side is 75, and then you also have to compare with the area with when you're choosing it to be I mean, look, if I tell you the perimeter is 300, what is theoretically, I mean, it sounds silly, but what is technically the largest x you could possibly have? What is the domain of our function a? The domain of our function a would be 0. That would really not be any rectangle because the length would be 0. And then the largest value that makes sense in this scenario would be 300. How many times are you going to sing that song up there?
What are you doing?
I'm still working. All right.
Well, I thought it.
Hold on, time out. Think about this and if you have any questions. What do you need, honey?
I don't know how to turn on the TV, and I can't find as many songs as I can on my iPad, and the TV is bigger to see all of it. And I was trying to dance like them, and I couldn't because it was too small.
Oh, okay.
So, and I was
Struggle's real.
back, so I really wanted to do. So I thought.
All right, I'll turn it on. Give me 1 second, guys. I apologize.
All
right, yeah, okay, come on. All right, sorry about that. All right, does anybody have a question about this so far? We're not done quite yet. Please, if you have a question where the 0 and the 300 come from, and let me just remind you, so the domain in this particular context, nothing else would make sense. No other numbers make sense. So that's why we're just comparing. Remember, we talked about this. When you have a fixed domain, you want to know the absolute global max and min. You compare all critical numbers with the endpoints. All right, so then all we have to do now is we have to compare these things. So that's what we're going to do. So you plug in, obviously you plug in 0, you get 0, which doesn't surprise us. You plug in 300, it's a little more difficult, but you can definitely do it by hand. And so let's do it. So A of 0 gives us 0, which doesn't make any sense. A of 75, if you plug it in, well, what are you going to get? You get 150 times 75, and then minus 75 squared. So you know it's going to be positive, and if you blah, 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 so what? I'll just cheat, 5625. And then lastly, if you plug 300 in, you end up getting a negative number. So what does this all tell us? What is the conclusion we make? The conclusion is so we conclude area is maximized if we choose x equals 75. And then this forces, if you do the math, this forces y to be 75 as well. So what we've actually shown is of all rectangles with a fixed perimeter, a square maximizes the area. So this is an example of a very and much deeper important problem in high-level mathematics called an isoperimetric problem, which is if I give you, if I say determine, if I say you have some perimeter, and it doesn't even have to be a rectangle, it could be any shape in 2 dimensions, what shape gives you the largest area? Turns out it's a circle in 2 dimensions. It's pretty cool. Okay, so does anybody have a question about this? Comments, concerns? All right. All right, let's do another one. So a box with a square base and no top must have a volume of, let's say, 10,000 centimeters cubed. Now, here's a very practical problem. Suppose we own some company or we manufacture products and we want to ship it. Say we're Amazon, although I don't think they're so rich, they don't really care. But if I need to ship something, ideally, if I'm in a business, I would like to ship it as cheaply yet as efficient as possible. So a very, very simplified version of that sort of problem is this. I want to determine dimensions that minimize the materials used. And in this case, we're going to be very simplified. That's just surface area. We're not going to worry about thickness or any strength. We're just a very simplified version of a real world problem. So once again, it's in our best interest to start drawing pictures. So let's think about what this box might look like. So we know that it has a square base. So if I try to draw this box, so what does this look like? It's got an open top, so I'll try to draw it like this. So we know the base is square, so we'll call these both X, and then the height can be different. We'll call it Y. We don't know yet. Maybe it's the same, maybe it's not. So that's one way to visualize our box. And by the way, we have some formulas for this. We are told some important things. We're told, for example, that the volume, which is x squared y, has to satisfy 10,000. So another way of writing this is that 10,000 over y is x squared. That's one thing you can do. Or if you wanted to, you can write it the other way, and you could say that 10,000 over x squared is equal to y. So there's a couple ways you can think about this. Now, another way of thinking about how this box might be constructed is if maybe you think about it being differently. You think about this box has how many sides? It has 4 sides and it has a base. So there's really 5 sides to it. So sometimes it might be useful for us to draw this thing a little differently. So maybe instead of drawing it this way, maybe I'll imagine I took scissors and I cut down the edges like this, this, and this. So I took scissors or a box cutter and I sliced down the 4 corners. And in that case, I can lay my box out flat on the ground. So if I lay it out flat, I have my base, which is x times x, and then I have my 4 sides. Here's side 1. Here's another side. Here's another side, and then here's my 4th side. So on the left, I have the box sitting in 3-dimensional space. On the right, I cut the corners and laid it flat. See, this is I guess if we're in a classroom, I could have brought a cardboard box in and showed you exactly what I mean. Either way, the surface area, which I'm going to denote as A, in either scenario, you can reason what the area is. The area is x squared, because there's one base, plus 4 times xy. So this is the function we want to really study. We are trying to minimize this. We want to spend the least amount of money as possible building this box. Does anybody have a question or a comment? Good. No, I'm just kidding. It's a shame. I don't know what any of you look like, really. I don't know anything about you guys. This online stuff stinks. It'd be so much more fun. Right now, I'd be kicking a box around the classroom. We'd be having all kinds of fun, laughing, telling stories about all the summer fun we're having. And instead, I'm sitting here looking at black screens, and I hear my kids singing songs on YouTube videos upstairs. What a time to be alive. All right, so just like in the last problem and in all of these problems, you have to use your constraint, the restriction in the problem, and you have to plug it into the function you're interested in. And the fancy word for that is the objective function. So let's say that. So to use calculus, what we'll do is we'll plug y equals 10,000 over x squared into the area equation to get a function. So my area equals x squared plus 4xy. And that implies that I can have a function now of x by replacing y with 10,000 over x squared. And of course, this simplifies. You get 40,000. And for easier for my brain, I'm going to write this as x to the minus 1. Because really, x over x squared becomes 1 over x. So I'm going to write it as x to the power minus 1. Does anybody have a question or a comment? Okay, so we want to use calculus. So what we need to do is determine any extreme values. So we want to minimize we compute. What is the derivative? The derivative is 2x, then it becomes minus 40,000, x to the negative 2. And so now we have to solve this equation. So a prime of x equals 0, provided 2x minus 40,000 over x squared equals 0. So just double check our work. Now, how do you solve this? This is an equation you would have encountered, and you studied how to solve these back in like algebra class. So this is equivalent to 2x cubed equals 40,000. So I multiply everything by x squared to clear the fraction. And that's equivalent to x cubed equals 20,000. Which means x is the cubed root of 20,000. So if you have a question about that, please ask. Comments about how I did that. So what we need to know, though, is this a minimum or a maximum? So we need to verify that it is a minimum. That's what we want. So to verify it's a minimum, so what do you want to use? You have two tests to verify it's a minimum or a max. Or if you want, you can just compare it with the endpoints of the domain. And the endpoints of the domain would be the silly case when there's no rectangle, or excuse me, no box at all, which of course, if you look at the formula for your area, when you plug 0 into that, doesn't make any sense. So you can't really do that. That's undefined, right? You can't divide by 0. What about A of the other endpoint, which would be 10,000? Well, what happens when you plug 10,000 into this creature? By the way, this is... Well, when you plug 10,000 and you get a very big number, hold on one second. Okay, I'll be up in a second. Lydia. Okay, stop. I'll be up in a second.
I keep
Lydia,
saying
I'm
videos
busy.
that I want on, and
Well, you're not saying them clearly enough. You need to articulate.
and it's not working.
All right, I'll be up in a
now
minute.
Ricky woke up.
All right, well, I'll be up in a minute.
Okay.
All right. All right, go play for it. Oh, go open Ricky's door and turn the light on, please.
No, you have to come get
Please.
I'm trying to get this remote to work. I'm trying to get.
All right, I apologize. We have chaos here. All right, anyhow, when you plug this in, I mean, if you plug, that looks ugly. What in the heck? That's 10,000. If you plug 10,000 into the area function, it's actually not terribly difficult to compute because you're just squaring things. But you end up getting a massive number. What is it going to have? So I'm missing 2 zeros. So it's huge. And then, of course, if you go and plug the number we want, which is the cubed root of 20,000, if you plug this in, look, you could do this. It's not hard. I shouldn't say it's not hard, but it's not difficult to get an estimate value of this, or you can do it precisely on a calculator. You know, there's lots of ways you can do this. But for example, if I plug it into I'm hitting the wrong button. Bear with me. If you plug this into a calculator, you get approximately 1105. Now, the problem in this particular problem is this is not good enough for us. Even though it's smaller than a of 10, since we can't evaluate a of 0, that extreme value theorem doesn't apply. And so we have to use either our first or second derivative test. So let's be very clear with that. So since So one of the things, and I don't know if this is, maybe you're starting to see this, you might think this is overkill. Some of you may have done this stuff before, and you may say, I'm really overkilling this verifying. Well, it's important because we have to verify that it is indeed a minimum. Just because it's a critical number doesn't mean it's a minimum. We have to verify it. Well, what you can do, though, is you can easily make a sign chart and reason that. So remember, what's the derivative here? The derivative is 2x minus 40,000, blah, blah, blah. So notice a prime of, just take 1. A prime of 1 is clearly negative because it's 2 minus 40,000. And you already know that a of 10,000 is something. So what if you did a prime of 10,000? Or even something a little, we need something bigger than the cubed root of 20,000. So I need to pick a number that's bigger than the cubed root of 20,000. Now you might say, oh, I don't know, what it is. Well, think about 20,000. You can get ideas from it just by studying 20. So the cubed root of 20,000 is a little bigger than 25. And you can reason that kind of stuff thinking about maybe the cubed root of 20. So what if I just take something like a prime of 30? What does that equal to? Well, if I plug it in here, I get 2 times 30 minus 40,000 over, say, 30 times 30 if I want. And then that 0 and that 0 cancel. This and this cancel. And then you're left with 400 over 9. So it's 60 minus what? Well, what's 400 over 9? Well, 400 over 9 is, say, well, we don't even have to compute it. You take 400 over 9, it's not hard to show that this is clearly positive. So what this shows us is that by the first derivative test, since the derivative changes sign, x equals the cubed root of 20,000 is a min. So that gives us the minimum value. If we choose our dimension to be x cubed root of 20,000, we minimize our area. Does anybody have a question about this? Comments, concerns? As you'll see, these problems are pretty, they're difficult, they're long. They take time to get used to. The more of them you do, the more examples you read in the book. If you go Google optimization problems, calculus, you'll find YouTube videos of these things. If you want to learn them, it's going to take some effort on your part. Any comments or questions about this? All right, well then let's look at, huh? I see that. Our next app. Huh?
The eye doctor was trying to put nerves on us.
Oh my God. All right, I'm in class. Your kids are already causing a scene. All right, here we go. So our next application is just a new name for the tangent line. So let's recall the tangent line. So the tangent line to f of x at the point a comma f of a is, you guys just did this on the test. What is it? It's y minus f of a equals f prime evaluated at a times x minus a. And of course you could rewrite this if you wanted. You can take f of a to the other side and you have this. So what we're saying is this is actually, this line is very useful, and it turns out it's going to be used for a few things. But if you've done any in consideration of our previous homeworks, and if you look at our test problem, and maybe you graphed, when we found tangent lines, you graphed the function with its tangent line. If you draw the picture, if you draw a picture of what this looks like, you see why there's some geometric sort of uses here. So if I draw a curve, and let's call this y equals f of x, and let's pick a point. So this is the point a comma f of a. So what's the tangent line? Well, let's draw it. So this is the tangent line. So here's the observation. So it's useful. So what we do is we denote the tangent line by L. L of x is, instead of calling it y, let's call it L of x. And it's the same thing. So the observation to make is the following. So if x is approximately a, then f evaluated at x is approximately L approximated at x. So again, ponder this. Pick a point that's close to A. So if I pick something that's close to A, let's call this X, then look at the point. The point on the pink line is very close to the corresponding point on the blue line. They're close together. Now, of course, when I'm not as close to A, if I'm over here, there's a bigger gap. But you'll notice that near A, the gap is small. And so for this reason, we don't just call it the tangent line, we give it a more descriptive name that is going to come into play later on in Calc 2 as well. So we give this guy the following name. So we call L the linear approximation of f at A. So we're just giving a new name to the tangent line because we're showing how descriptive it is. And there's actually a lot more happening here that maybe you've thought about or not. A cool thing that this is also saying is that any curve can be thought of as made up as a bunch of straight lines. And perhaps you've thought of that before in your life when you say, oh yeah, we're on Earth, this big sphere-like thing. But yet when you walk down, when you walk from one side of your kitchen to the other at your house, you don't feel like you're walking on a curve, right? Because your size relative to the size of the Earth is so small that even though we're on this massive sphere-like thing, you don't realize that. Everything seems straight to us. Of course, when you go up hills and stuff like that. Does anybody have a question about this before we do one? We asked you to do this on the homework. Okay, so let's do an example. So determine the linear approximation of f of x equals the square root of x at 25, 5. And then let's use this to approximate the square root of 27. So how do we do this? Well, the first thing, if we want to compute the linear approximation, we need to do some calculations beforehand. So that is, we need the derivative. The derivative is 1 over 2 root x. And we need the derivative evaluated at 25. And when we plug that in, we get 1/10. Thus, what is L? L of x is f evaluated at 25 times x minus 25 plus f evaluated at 25. And so when you plug everything in, you get 1/10 x minus 25 plus 5. So this is your linear approximation. So the first thing we got to know is, does anybody have a question about how we got this? Okay, so here's what we know. We know that this line is a good approximation for the square root curve, at least near 25, 5. And so what we're going to do is we're going to use that to our benefit, and we're going to sort of do some approximations. So if we look at the graph, we will see that L of 27 should be approximately f of 27, since 27 is, relatively, it's approximately 25. So what does that mean? Well, L of 27 is being approximately the square root of 27. That's the same thing as saying that the square root of 27 is approximately what? We'll plug it in. We had 1/10. Then you plug 27 in, so it's 27 minus 25 plus 5. And you're left with 2/10 plus 5. And so what you can do is if you do the arithmetic here, you get that if you combine this, this is 26 over 5. So what do you conclude? Well, if you use a decimal, the square root of 27 is approximately 5.2. Now, is that a good or a bad approximation? Well, that's left to be decided, but it is an approximation. Any comments or questions about this? Going once, going twice. So when I say looking at the graph, what do I mean by that? Well, let's look at the graph. So let's share this, new share. So the function we were interested in was y equals the square root of x. We were interested in what was happening at 25, 5. So let's zoom out and check that point out. And then we found the tangent line. The tangent line was y equals 1/10 times x minus 25. And then it was plus 5. So if you look at this, look at that green line is for all intents and purposes right on top of the red. In fact, when I zoom in, it's really hard to distinguish if there's even a red curve there. As I zoom out, I start to realize that there's a red curve and a green line, but it's not clear when I zoom in. And so that's why we say this is a linear approximation. And then you can even compare the actual values. If I make a chart here, what's the actual value of the square root of 25, at least rounded more accurately, or 27? So we got the approximation of 5.2, which is, if we round the actual value up, is pretty accurate. Does anybody have a question? Comment? All right, well then I think we should leave it at here. And then I really hope that you guys work on these problems and you ask questions, particularly all these the intervals of concavity and increasing, and then those word problems. If you have questions, please reach out. Also, if you have questions about your exam score, and you want to talk about it, please reach out. And then don't forget, next week is our last week. So does anybody have a comment or a question before we end this funness? All right, I apologize for the couple interruptions. My kids don't listen that well. So, all right, guys, thank you very much. Take care. I guess I will talk to you guys next week, if not sooner. All right, take care. Be safe. Thank you.